I sort of stated this, this sort of analytic theorem, which we were going to prove, or at least give the idea of the proof today, and we used this to construct lots of meromorphic functions on a given closed Riemann surface. So just to remind you what the theorem is, right? We fix a closed Riemann surface X and a closed and connected. This is important. Riemann surface X and a smooth real value 2 form X. So just make it real value just to be not work in the complex world. Then the claim is then the claim is there exists a smooth function u in smooth functions of x, such that the Laplacian of u is equal to x, of rho, if and only if the integral over x of rho is equal to 0, and the u is unique up to addition of a constant. Okay, so then, right, so the point is this is essentially sort of 3 parts to the statement. So the first part is that there, given such a rho, there exists such a u. The second thing is if there exists a u, then rho has to satisfy this integrating to 0. And then the final part is that if there is a u, then it's unique up to addition of a constant. So as I mentioned last time, I mean, 2 of the 3 are kind of trivial, right? So if there is a u, then the fact that rho has to satisfy this follows immediately by Stokes' theorem. So that's fairly trivial. Similarly, if you have a given u, the fact that it's unique up to an addition of a constant, that's also not so hard to see. So you could either prove it by using the so-called maximum principle, or you could use the following integral identity, which is that the integral of u, Laplacian u, right? So this is 0 if u is harmonic. So let me put it another way to make it clear. Let's say Laplacian u is equal to Laplacian u prime is equal to rho. Then we have the integral identity that the 0 is equal to u minus u prime Laplacian u minus u prime. But we mentioned that this you could integrate by parts, and so then this was the same as the this Dirichlet norm up to a sign, right? But this was supposed to be this is a number with a sign, so the fact that it's 0 means that this has to be 0, and so you conclude that this implies that u minus u prime is constant. Okay, so that's so you could also think about it by saying, well, this is harmonic, and so then it has a maximum principle. It's another proof you should think about. Okay, so that's the theorem for Riemann surfaces. So, I mean, I should say, like, of course, you know, in the context of a Riemann surface, we're of course allowed to think about everything in terms of just the Riemann surface structure. Like, we get this natural Laplacian, but of course, you know, if we have a metric G, then by looking at the, say, compatible Riemann surface structure, right, we can see that this equation, Laplacian G of u equals to rho, where now rho, this is supposed to be a C infinite function on, say, x. Right, this should have a solution. Now the integral over x of rho times the volume form of G is equal to 0. Okay, right. So this is, you should try and see why these are kind of equivalent notions. But of course, the point is this we can imagine this making sense for any Riemannian manifold that's, say, closed and connected, and one would expect that this should generalize. Whereas obviously this is special to dimension 2. Okay, so that's the setup for that's the theorem we want to prove. And then I probably won't. I'll probably just maybe briefly discuss this next time. But right, so we have this condition that X be closed. So to actually prove the uniformization theorem, we want to use a variant of this when X is non-compact. So you might, let me just state a result, which is right. So if X is not, if X is not closed, then the same result. Well, let me be a little more precise. So not the same result, but rather, if his rho is not closed, then if this integral of rho, let's assume now. So we assume now then if rho has compact support, right? So it's 0 away from a compact set, right? Which is automatic in the closed case, but we need to assume it now. And the integral of x rho is 0. So this has compact support, so this makes sense. Then this implies there exists a smooth function u such that Laplacian u is equal to rho. And we can make some additional assumption, which is that u is 0 at infinity, i.e. For all epsilon greater than 0, there exists a compact k epsilon compact such that u is less than epsilon on x minus the compact. Okay? Okay, so this is in a sense, this is one direction of this guy. I mean, this is a kind of generalization, but of course it's a weaker theorem because we only get one of the directions. Though, and this, of course, this is vacuous on a closed surface. So you should maybe, just to understand this, maybe this is a useful exercise. So think about x equal to the complex plane and x equal to the unit disk. You should try and convince yourself that that on the complex plane, at least, you need this condition, but you don't need it on the disk. So in the non-compact setting, things are a little less clear cut. But I don't want to dwell on that, so maybe I'll leave that as an exercise. So. Right, these are very explicit, so you can think about them. Okay, so that being said, let's try and talk about how we're going to prove this, right? So this is a statement in, I mean, the thing we need to prove. So we want to show sort of the existence of u given rho. Okay, so this is this falls into the framework of trying to kind of solve a second-order elliptic equation. So in general, I mean, how do you solve a PDE? I mean, you have to do some work, but in this case, we have what amounts to an inhomogeneous linear PDE. So it becomes much simpler there. So the idea here is we're going to do two steps. So the first is to establish the existence of a weak solution. So it makes precise what I mean to let's call, well, right, so what does this mean? So Aaron mentioned this a while ago, but what this means is we'll establish the existence of a solution in some kind of distributional sense. So the U will not necessarily be a smooth function, but it will be something we can integrate compactly supported functions against, and we'll sort of interpret this based on what integration by parts tells us to look at. So this uses sort of abstract theory, since we're in a linear setting. Right, so it'll be some theorem in functional analysis, what it'll boil down to. So the second part is then, this is always the crucial part in some sense. The less straightforward is to establish the regularity. I don't know why I'm putting that in quotes. Regularity of the weak solution. Okay, so we found this weak solution, and now we want to show that, in fact, it's a smooth solution, smooth function, and so classically solves this equation and gives us the desired U. So in general, this is a fairly robust methodology for linear equations. The regularity, though, is of course something special, and has to do with the fact that this is an elliptic equation, so has certain smoothing properties. Though, I mean, this is, of course, elliptic regularity is fairly, complicated. I mean, it's not complicated, but there's a lot of moving pieces, and, to do it in the full generality is a bit involved. But luckily, this operator will be is fairly simple, so there's a kind of elementary approach to the regularity theory, which I will try and sketch. Okay, so what's the first part? So let's do this first part. So let's do the sort of existence. Okay, so let's try and just set up a little bit of abstract language. So hopefully this is somewhat familiar. Right, so remember, right, we're never going to be able to solve this operator uniquely because of this addition to constants. So what we want to do is sort of make sure that there's nothing, if we can find a solution, that it should be unique. And so the way to do this is sort of to kill the kernel of the operator. So we're just going to define this this linear space, which will be the smooth functions on the Riemann surface, where we mod out by the constant functions. So these are the constant functions. So we're sort of always going to use the fact, and we'll sort of use it implicitly, that this can be identified with the set of C infinite functions of x with integral 0. Okay, so what do I mean by saying it has integral 0? Well, what do we need to know? We can't integrate functions, so that means, this identification depends on some choice on, this depends on a volume form. Right, so of course in, say, the Riemannian setting, we get the volume form from the metric, but otherwise we can choose it. And the point is that we get some identification, which we'll often make, even if we're not super explicit about it. Okay, so now... Sorry? Sorry, yeah, I should say this is just a remark. I'm not going to talk in detail about that, so I'm just doing the compact case. Yeah, so of course if you're in the non-compact case, then you need to kind of restrict to things that have, say, compact support to even make sense of this. Okay, so yeah, okay, so we're considering this this linear space, and remember we had this right. We introduced this on the space of functions. We introduced this sort of inner product, which was right. We said if f and g were C infinite functions, right? We introduced this sort of Dirichlet inner product, which wasn't quite an inner product because, of course, it was it was degenerate. So this was the integral of f of essentially, I think it was, you take the 1, 0 part and you wedge it with the 0, 1 part. And maybe there's some constant, which I don't remember. Some constant. Right, so the point about this is it was degenerate since, of course, you put a constant in and you get 0. But the point is it descends to an inner product, which we'll just let, isn't honest. Okay, and so then the point is that we're going to take H. H will just be the completion, the Cauchy completion of H0 with respect to this inner product. So again, if you fix a volume form, essentially this is sort of the first Sobolev space of the surface where you mod out by constant functions. This is H1. And again, in principle, like the way we've defined it, this space depends on our choice of Riemann's surface, right? Right, because this inner product depends on the choice of Riemann's surface. But one thing you should convince yourself is that, at least on a closed surface, actually this space can be made sense of independent of the choice of Riemann surface. We don't need that, but it's useful as an exercise. In other words, if you have a different choice of Riemann surface on the same manifold, then you get an equivalent Hilbert space. Okay, but right, we don't need that, but right. So the tool we're going to use to prove the existence is going to be based off of this sort of integration by parts identity, and then this theorem from functional analysis. So just to remind you, this is a theorem. So this is the Riesz representation theorem. Right. So this is just a generalization to Hilbert spaces of a kind of classical linear algebra fact. Right. So the idea is that we have if H is a Hilbert space, a real, say, Hilbert space. For instance, the H we just constructed over here, and sigma takes H to R is a bounded linear operator. Right, so we have the inner product, so we have a norm, and that just means that sigma of an element x, this is the inner product on R, this is the norm on R, is just less than some constant x h, then this implies that there exists an element z in H such that sigma of x is equal to the inner product of z and x. Okay. So what I want to convince you first is that this element z is supposed to be our solution to this equation in the weak sense. And just as a remark, you probably have seen this, of course, right? Being bounded, we don't need to specify the operator on all of H, right? It's enough to specify the operator on some dense subset. So, for example, H0. And if you can prove that this boundedness holds on the dense subset, then just by construction, it's easy to extend it to all of H as a bounded operator. So we're really just going to, when we work with our operator, we'll just think of the H0, the dense subset. Okay, so the claim, I mean, just to sort of see how we can turn our solution over there into this type of problem is, well, I'm not a claim, right? So then let's just assume, say, just for, if you really existed, as a C infinite, function, then if we did everything correctly, right, we would see that that by integrating by parts, that if you took the integral of x of psi of rho minus delta u, then this would be equal to 0 for all psi, right? Because this to be a real solution would mean this is 0, and so then we would it didn't matter if we multiplied by any compactly supported function or any smooth function in this case, since we're closed. But of course, I mean, the point is we can integrate this by parts, and so this is supposed to be the same as the integral of psi rho. And I guess, assuming this is where I feel like I might have, I don't remember the convention I chose, but I think we chose this to be, I think I chose this to be a positive operator, but, sorry, I think I chose this to be a positive operator, but somehow in my notes it now is a negative operator. So let me just go with the notes so I don't get myself too confused, but wait, no, this is saying it's a positive operator, which is so I think before I might have had it as a negative operator, and now I have it as a positive operator. But right, so you should understand that, right, there's some ambiguity of when you do the integrate of the sign. The L'Hopital can be plus or minus this. The conventions are never the same, depending on who you talk to. And depending on what the plus or minus is, you'll get a different plus or minus here when you do the integration by parts. It won't affect anything. It's just I'm just going to do this because it's what's in my notes. Right, so the idea is, right, now this is supposed to make us think of this inner product over here. Right, so D. So the idea is, right, if we define a function, we define a map rho hat, which is taking C infinite. Well, let's just call it H0, which of course is C infinity mod constants to R, right? By just saying we send a function. Psi to the integral over x of rho psi, which, right, here of course this makes perfect sense for smooth functions, but the point is, because of our assumption on the integral of rho, this descends to this quotient. So this is a well-defined function. So if we can show that this is bounded, this is a bounded operator, right? So in other words, just show that i.e. that rho hat of psi is less than or equal to some constant times psi d, then we can use this, then u, right? Then essentially we interpret this identity as the Riesz representation theorem. So then the Riesz representation theorem gives a candidate u in H, right? And the goal of right? So the goal was, of course, that we really want this to be we really want this to be in H0 to have regularity, but for the time being, it's just an abstract guy. So, and again, you should think of this as, it's a Cauchy completion of something we understand, so it's just a Cauchy sequence of reasonable functions. Okay, so right, so that's the point. This is what we mean to say this element in H is if the inner product of the element in H with every test function psi is equal to this guy, then we have basically found the weak solution at least, and then the idea is to prove that it's actually a strong solution. Okay, so now what's the one remaining piece we have to do to make this existence part correct? So we need to prove that the operator is bounded. So we need to prove. So we need to show. Okay, so the key, and maybe I'll make this as an aside. So the key tool is a we need some relationship between. This is sort of since this is a smooth function, this is controlled, for example, by the L1 norm of psi, and certainly by the L2 norm of psi, by the Cauchy-Schwarz inequality. So to prove this is a bounded operator, we need to kind of relate the L2 norm of psi to, say, this norm, this Dirichlet norm, which is a kind of energy norm. So if you're familiar with these things, this is an example of a Poincare inequality. Poincare. Okay, so the Poincare inequality usually comes in two flavors. So the observation is that, of course, if we have a function and we add a constant to it, then the energy we don't change the energy, but we do change the L2 norm. So just in general, we can't kind of we can't use the L2 norm of the energy to control the L2 norm of the function because we can add a constant. So the Poincare inequality, we need to add an additional ingredient, which is to sort of kill, in a sense, this freedom to add a constant. So there's usually two ways to do that. So on the one hand, we could sort of demand that the function have compact support, because then obviously we can't add a constant to it because that would destroy the compactness of the support. The other way is to sort of demand that it be sort of orthogonal to the constants, which again you can't add a constant because that would destroy being orthogonal to the constants. And in general, you'll get different values of the inequality, and they behave slightly differently. But I just wanted to point that out. So we're going to use the one where you're orthogonal to the identity, because that's sort of closer in spirit to what we're working with, and it's the one that, in a sense, on a closed surface is the only one that makes sense because every function has compact support, so you can always add a constant to it. Okay, so the idea here is the following theorem. So let's fix omega inside of R2, right? So rather than do it, we could try and do it directly on the manifold, but that would require more theory. So we're going to just do it in charts and prove that we can patch everything together. So let's say this is an open bounded domain. Okay, so the theorem is that. So the theorem is that in general, that if we have a say C infinite function of omega, if the integral of psi is equal to 0 over omega, then this implies that the integral over omega of the L2 norm of psi is controlled, with respect to the area form, is controlled by a Lebesgue measure, is controlled by some constant that depends on omega times the gradient of psi, so the Dirichlet energy. Okay? So the point, though, is the constant C omega depends on the geometry so in fact, to prove it for a general domain, we need to go through some theory we don't want to use. So it turns out that if we're actually going to just restrict to a convex open domain in our proof. But I just want to say that the theorem holds the same. It's just in the convex case, there's an elementary kind of calculus proof of this fact, and we also get a kind of nice estimate on this constant C omega, where in general it's very hard to say. So just as a an example, we'll prove that. So we'll show that C of omega is on the order of some universal constant divided by the diameter of omega squared, which is everything should scale. You should recognize how things, when you rescale the domain, everything changes. And you should see that this should scale roughly like 1 over the length squared, if I did everything correctly. Sorry, it should be the other way around. Diameter. So it turns out that, in fact, if you just want to use the diameter, you can actually prove that this constant, that you can figure out the sharp constant here, which is essentially turns out to be pi squared. Oh wait, now I'm confused. Let me just, sorry, so the energy is scale invariant. Yeah, so this is correct. But right, you could ask. So it turns out that actually the C, you can figure out what the sharp constant is, and that's a sort of interesting problem. And it turns out when you look at the diameter, the sharp constant is sort of achieved on a domain that kind of collapses to an interval. Another question is where you could sort of, instead of using the domain, you could use the area, and then the sharp constant is achieved on something that is the unit disk. So there's a lot of interesting theory here that we won't use because we only need that there's some constant. But you should definitely think about what possible constants. And as I said, when you're not convex, you're not going to get a uniform constant. So maybe as an exercise, you should try and figure out what the constant is for this sort of domain, which is clearly not convex, where this epsilon, this is, say, unit length, and epsilon is going to 0. I think that's a useful illustration of how this is measuring something about the geometry of the domain, or even more fundamentally, something about, say, the connectedness. Okay, so that's the theorem we need. So let's give a proof of it. As I said, it's just a calculus fact, in some sense. So that's good to see. Oh, and again, of course, maybe I should just say this in words, right? If we don't assume psi integrates to 0, we can take any function and we just have to subtract off the average value, because then we know it integrates to 0. So in general, we can also write this where we subtract off the average value. Okay, so let's just prove this inequality. All right, so what's the idea? Right, so we start with our psi, and so then we look at the integral over omega of f squared, right? So this is of x. So this is the quantity we want to control. And we rewrite this as two separate integrals of the same thing. Not A. Wait. Okay, so we just split this into two copies of itself, where we just change the variables. But the observation is because, and let's, oh my God. All right, so f is equal to psi. So, okay, so f is psi. So we know that integral of f over omega dA is equal to 0. And so then we can combine this into one double integral by saying that this is 1 over 2 times the area of omega of the integral over twice the region omega of f of x minus f of y squared dA of x dA of y. Okay, so that's just rewriting the integral and using the Fubini's theorem. And right, I mean, the point is we're getting an extra integral, so we have to divide by the volume. Okay, so then the point is we want to kind of relate this guy to the gradient, right? So that's just the fundamental theorem of calculus plus the convexity of omega. And you can kind of see in what I just am about to write, you could kind of see how you don't really need the convexity anymore, but once you drop the convexity, you're going to lose getting we're going to get a very explicit constant, whereas you'll lose that, and you should think about why you lose that. So the point is we get that f of x minus f of y squared. Sorry, well, let's put it without the squared first. So just the difference of these guys is the integral from 0 to 1 of x minus y dot the gradient of f evaluated at tx plus 1 minus ty. So we're just combining the points x and y by the convex linear combination dt. Okay? So this is just the fundamental theorem of calculus. So the point is, of course, we could take, I mean, as long as the domain's connected, we can choose some other path connecting them. But of course, where we're going to try and estimate this, well, the various properties of the path will come in. But in the convex case, we can just take the line segment connecting them. Right, so then just taking the Cauchy-Schwarz inequality, we get the estimate on the square of this. Right, we just apply Cauchy-Schwarz, and now we see that this is just this is bounded above by the diameter. So we get that this is less than or equal to the diameter of omega squared plus the integral from 0 to 1 of the gradient of f squared of tx plus 1 minus ty dy. Okay? So now what we're just going to do is just, take this double integral, take the double integral over here, and then do a bunch of, rearranging the integral. So maybe I won't do all the gory details in the interest of time. Right, so, but if we plug this inequality into the double integral above, right, we're going to essentially work out that, and go through all the steps, we're going to end up with essentially, 1 over, we're going to end up with the integral over omega of f squared of x dAx. So I'll just write down essentially this is going to be, if you plug this in, go through some steps, and maybe I'll just put an intermediary step because it's sort of maybe enlightening. So it's going to be the integral over omega of I don't know how enlightening this is. Maybe I'll leave this as an exercise. So just plug in this integral and play around with it, and you'll end up, hopefully, with the following constant, which is that you get f of x squared dA of x is less than or equal to some constant d of omega squared, diameter squared, over 2 times the integral over omega of the gradient of u f squared of x dA of x, where here this constant actually is fairly explicit, is given by the integral from 0 to 1 of the minimum of the values 1 t squared over 1 minus t squared times t to the minus 2. So this is this is singular, but when t is small, but this exactly cancels with this. And then when t is near 1, this is nice. So this actually is a nice function, dt, which is, of course, less than infinity. OK, sorry about that. But, so again, this is just the elementary calculus to get from here to here. And this is the result we wanted. And again, as I said, you could sort of think about how to generalize this proof. What ingredients do you need to make it work, and see how you could maybe get an estimate in other settings where you don't have such an explicit constant. Okay. Okay, so now we want to use this to prove this theorem. So as I said, what we're going to do is just work in a coordinate chart. Okay, so let's go over here. Okay, so now let's try and use this to prove. So let's start with the simple case. Let's simplify and assume, for the time being, that the support of the two-form rho is inside of U, where we have a coordinate chart Z taking U to U tilde inside of C, or equivalently R2 as always, where this is now going to be some convex. We can always shrink everything to make this convex, a convex open set. Okay? And so now the support of this is supposed to be inside of U, and so we can pull everything back to U tilde and work in the coordinates. So we pull everything back to U tilde. Right, and one of the things we were supposed to sort of observe is that this Dirichlet energy of the Riemann surface in this holomorphic coordinate chart was sort of the same as the normal Dirichlet energy of the Euclidean space. Right, so, and of course in Euclidean space we also have this. We have the volume form coming from Euclidean space and Lebesgue measure. So everything is sort of explicit in that case, and so we can think of. We can think of, in the chart, we think of rho as the function rho. So the idea is the form rho is sort of rho dx wedge dy. And so then the operator rho hat, right? Rho hat is, of course, and again, we use this identification I mentioned before, which says that we identify the elements in space of H0, we can sort of think of, or at least in H0, we can identify with elements that are smooth functions on U, say with integral 0, or we just make some choice. It doesn't really matter. So the point is, rho naught of psi then is just going to be the integral over U of rho psi, where now these are just functions, dx, dy. If assuming everything has worked out correctly, which it should have. So the point is, we're now trying to get an estimate on this guy, right? But the idea is we can think of, well, I think maybe to be more precise, right? So we think of psi as an element of H0, right? And then we can think of psi restricted to the chart U as also an element of C0. But the idea is, when we think of it as C0, but we had to make some choice to identify C0 with C infinity with H0, sorry. So the point is, we can just think of psi as being inside of C infinity of U, but the way it doesn't make sense necessarily to assume that it has integral 0. The idea is we start with the element in H0 on the whole manifold, then we choose some representative, which is a smooth function on the whole of X, and then when we restrict to the chart, we just restrict that function to the chart. So we don't necessarily assume anything about it having integral 0 on the chart. But the point is, because rho has compact support and integral 0, this operator didn't matter what choice we make. So this is well defined, independent of this. Right. So this is well defined. Well, still well defined. Right. But the point is then, again, because it's integral 0, we can replace this with rho times psi minus psi bar, where psi bar is the average. Right. And again, this is now functions. This is a function with integral 0. This is a function with smooth function of compact support. Everything's smooth. So we just do the Cauchy-Schwarz, right? This is some constant that depends on rho, but rho is fixed, and then it's going to be psi minus psi bar in L2 of omega, right? But now we can go back to our Poincare inequality and say this is less than or equal to some constant rho, constant omega of the gradient of psi in L2 of omega, right? Right. But the point is, again, if we did everything correctly, computing this gradient here is the same as computing sort of a restriction of the Dirichlet energy. So since this is, if we just anything outside of the chart is just helping us, this is going to be less than a constant rho constant omega times this Dirichlet inner product, right? And that's exactly what we wanted to show. Is now we've shown that the operator is bounded on H0 and hence extends to a bounded linear operator on H, and we can then use the Riesz representation theorem to find the desired element Z, right? Okay, so everyone happy with that? Maybe not. But the point now is then we want to then use this localized theorem to prove the global theorem, and luckily we have a clever little trick in this particular case. Okay, so now we want to go to the global setting, to the actual theorem, at least the existence part. So the idea is we now just pick some gamma alpha, a partition of unity, such that the support of each gamma alpha is contained in a chart as over there. Right. And so what we'd like to do is we'd like to localize rho by multiplying by the partition of unity, right? But of course, if we multiply by the partition of unity, we'll get something with compact, we'll make the support of rho nice, so it'll be inside the right chart. But of course, we won't have that the integral is 0. So we're kind of can't quite do that, but we can do something a little clever, which is, of course, the fact that the integral of x of rho is equal to 0. This implies that rho is equal to d of theta, right, for a one-form theta. So hint, by the way, right, I assume that x is connected, and I have where, you might wonder where I've actually used that x is connected, and it's exactly here that I use that x is connected, right? So this is not true if x is not connected. And you can think, I mean, the theorem can't possibly hold if you have two components. It's have a volume form on one component and minus the volume form on the other. So this is where the connectedness comes in, and this is using the fact. So the fact that the integral is 0 means this form that's automatically closed because the top form is exact. And then we just let rho of alpha be equal to d of this gamma alpha theta, right? So then the point is the rho is equal to the sum of the rho alpha. And since everything's closed, we can just make this a finite sum. And the point is now the rho alphas are exactly like that, so we can find the desired element z alpha and then sum them up to get the right. So this gives so then we can use this to find the desired u. Okay, so that's the proof, okay, of the existence part. So I have about 10 minutes. So maybe I'll just briefly discuss the regularity, and maybe come back to it a little bit next time, or maybe have you guys do some exercises. Okay, so now we want to look at the regularity. Okay, so right. So the idea is we found this object u, which is an element of H, and that sort of has the idea that this rho hat of u is equal to of psi is equal to the Dirichlet inner product of z and psi for all psi that are in H0, say. And the point is, well, how are we supposed to think of u? So one way of thinking of u is there's a sequence of ui's going to u in H, ui's in H0. And so what this is, these are both sort of linear guys, so we're supposed to interpret this as saying that the integral of rho ui is equal to, the Dirichlet, well, let's just say it's this way, it's equal to ui Laplacian psi. Psi. Right, in other words, the integral of rho minus Laplacian psi doesn't make any sense. Right. So the point, though, is that we have this for these ui's, right? But if we could, if we knew that ui converged in some, nice, like an L2 to something, right? This actually would make sense for the limit u, right? Just as they'd be represented by functions that it would make sense. So. The point is, the first thing we established, which I'll probably gloss over, but is that in fact this is true. So, of course, what is L2 of x? Right, L2 of x for us is just going to be functions. So in a closed surface, this is just L2, but functions which are locally L2. So this is convenient to talk about for the general theorem, which I mentioned. So these are functions which are locally L2. So i.e. in a chart. So you restrict the function to a chart, and you can just check by definition whether it's L2, and then you have to convince yourself that that's an invariant definition, but it is. So So what one can prove, just, I mean, there's a kind of, if you're on a closed manifold, you can just use the Poincare inequality on a closed manifold, which we could have done all of this with in any case. But then you could prove that actually the convergence in energy means that if we choose the right representative, which should be the kind of make these to have integral 0, then we get this convergence in L2. We can also give a kind of proof that holds also in X, that where these elements in the energy space actually converge locally in L2 to some limit u, which is locally in L2. But in any case, we get this, this function u, which is an L2 function and sort of satisfies this identity weakly in the sense that this makes sense. So this is true with u. So the claim, which is that, so the claim is then that actually u is a smooth function. Let me just summarize what I kind of blathered on about. So the claim is, first of all, that we can choose we have these elements ui, and we can write them as the class of some psi I, where psi I are in now just actual smooth functions of x. And so what we can assume is that the psi I converge to some psi in L2 loc of x. Okay? And the point is that u is in some sense, though we won't make this precise, u is sort of the class of psi. Right? And then that's what I was sort of blathering on about before, about this part. So we have to make sense of this, which I'll leave maybe to an exercise. But then the other part is that the psi, now what we're supposed to conclude from all this is that psi satisfies the following weak form of the Poisson equation, which is that the Laplacian rho psi is equal to the integral over x of psi. Oh, psi is terrible. Let's call this f. So rho psi is equal to Laplacian psi f for now psi, just smooth functions of x. So if compact support, but that's vacuous since we're considering the closed case. So then the claim, and this is the claim is that this implies that actually f is smooth. Okay, so here f is just some function in L2 with its. I mean, it's a little bit better, of course, because it's really. I mean, it's in L2, but it's actually in our construction. It's actually in a better space. It's in H, but so it has L2 Dirichlet energy that's finite. But in fact, I mean, this theorem. All we need to think about is it being in L2, and then we're going to conclude that it's smooth. So this is a consequence of what's known as the Weil's lemma. So Weil's lemma is the same observation, but where we have rho is equal to 0. So then if you have a function that's weakly harmonic and in L2, say, or even distributionally in L2, and distributionally harmonic, then it's actually smooth. Okay, so I'm out of time. So maybe next time I'll just briefly discuss how to prove this regularity, and then also indicate maybe the main ingredients of the proof of the uniformization theorem. And then we'll move on to minimal surfaces after that.